Welcome back to my channel, and as always, thanks to my subscribers. In this video, I want to show how you can use simple classes to build more complex classes. As in my previous video, I will be using the Arduino Integrated Development Environment, or IDE, to build the code. But this time, I will use the Arduino to control this three-color block signal. This signal can display any combination of green, yellow, or red lights, with the restriction that the green light is always on top, the yellow light is always in the center, and the red light is always at the bottom. So let's see how we can define a C++ class to control this signal. We will start with the classes for sketch we finished in the previous video, and as before, we'll rename it to classes 5. We'll delete lines 118 through 128, and we'll delete the code in the setup and loop functions. Now it's time to define the signal class. As before, we need a class constructor, and since the signals have 3 LEDs, we need to specify the 3 output pins. As with the LED class, we should also provide a second constructor, which will allow the specification of either common anode or common cathode. Next, we need a function to set the aspect we want the signal to display. Finally, we add the refresh function, which will manage the LEDs. For private items, all we need to provide are the 3 instances of the LED class called objects in our signal. So let's try this. When we check this code, we get an error as shown here. It turns out that signal has been defined elsewhere as a macro. A macro is sort of like an inline function, which is resolved at compile time. In retrospect, I should have chosen a different class name, but I'm too lazy to change all my typing, so all I need to do to fix this is to undefine signal, like this. And now the code checks out fine. But when we try to write the class constructor, we encounter a problem. I have not found any way to initialize our 3 LED objects. The private data members, green, yellow, and red, have had space allocated, but the LED class constructor, which you will recall did some important work, has not been invoked. To fix this, we have to declare pointers to 3 different LED objects. A pointer is just an address, and in C++, all pointers occupy the same amount of memory, regardless of the size or type of the object they point to. So now we can write our constructor function, which is incredibly simple. All we do is to create 3 new LED objects and store the addresses of these objects in the private data members grn, ylw, and red. Recall that the LED class manages all the overhead of remembering pin assignments and of setting the pin mode of the various pins. While we're at it, let's write the second constructor. And finally, the refresh function. Checking the code shows that I forgot to declare the return type for the refresh function. Once that's fixed, everything should be fine. But it's not. The error message has given us a great big hint. Instead of green dot refresh, I should have used green arrow refresh. This is because green is a pointer, which can point to any LED object. This is a subtle difference, which will trip you up time and again until it just sinks in, which may be why the compiler provides such a helpful error message. Once I fix this, the code compiles without errors. All that remains is to write the set aspect function. Since I modeled the Rio Grande, I will use the aspects shown on this web page, which was taken from the 1965 edition of the Rio Grande Rules of Operation. You, of course, are free to choose the aspect definitions of your chosen prototype or to make up your own. Given that each of the 3 LEDs can be on, off, or blinking, this list represents just 5 of the 27 possible combinations. We could easily program all 27 if we wanted. I'm not going to bore you as I type in all the aspect definitions and implementations. You can study the final code at your leisure. With the set aspect function complete, I hope you can see how we used the power of classes to make it much easier to program the behavior of complex objects. Now let's put it all together. I'm going to create 2 global objects, one for each of the 2 signals I've connected to my Arduino Nano, and I will create them in 2 different ways to illustrate the difference between early binding and late binding. But first, notice that so far, global variables use 9 bytes of dynamic memory. The first way is how we've declared objects up until now, and it employs early binding. That is, the storage for the object is allocated at compile time. We declare the object S1 by calling the constructor, and we invoke procedures using the syntax shown. Note that global variables now use 25 bytes of dynamic memory. Our signal object has used 16 bytes of memory. The second way is how we had to declare the subordinate objects in our signal class, and it employs late binding. We declare a pointer to the object, and then we assign a value to that pointer, which is returned by the constructor. Storage for the object is not allocated until runtime, and that's why it's called late binding. We invoke procedures using this syntax. Note that the global objects now use 27 bytes of memory. The S2 pointer only uses 2 bytes of memory. The 16 bytes required by a signal object will be allocated at runtime. These two ways to create objects are functionally the same. There are 2 reasons why you need to understand the difference. First, because there are times when you must employ late binding, as with our signal class definition. And second, because you might need a temporary object and memory space is limited. Late binding allows you to free the storage used by that object. And now for the moment of truth. I upload the program to the Arduino and watch the signals display the specified aspects. Obviously, the next step is to decide what will cause these aspects to change and to program that behavior into the Arduino. But that's a task for another day. Also note that I could just as easily create a class to control a 6-light signal, like this one, to provide aspects such as red over blinking yellow, meaning diverging approach medium, red over yellow, meaning diverging approach, or red over green, meaning diverging clear. Now that you understand how to include objects as members of classes, you can create any class hierarchy you like. For example, you might want to create a class consisting of 8 objects, 4 turnouts forming a double crossover, and 4 signals controlling traffic through the double crossover. C++ classes make this easy. In the description below this video, you'll find links to many of the products and tools I've mentioned. As always, I love to read your comments and to respond to your questions. If you want to see more videos of this type, be sure to subscribe and hit that like button. Thanks for watching, and I'll see you next time.